Hello and welcome to the Methods 3 and 4 Headstart lecture. My name is Dash, and today we are going to go into the details of Unit 4, the key topics you're going to go over. This is, of course, the middle set of lectures. There will be one at the end of the year as well. But today we're really going to take a dive into statistics and get your head around them, get an in-depth look so you have the understanding so that when you get to this course content, you are going to have a really good understanding and be able to absolutely ace those external exams like we both know you can. So there's several resources available for free at ATAR Notes. And as a student, I use and abuse these resources. They were absolutely fantastic. I don't recommend them enough, to be honest. It's a way to really do well on your externals and even your internals is to use the resources we have available. We also have paid resources, which is really high value stuff. Tute Smart, where we do some tutoring, study guides, Ed Unlimited. We do have tutoring available, so if you would like help week on week with your course content, assessments, etc., do get in contact via our website. I am a tutor, for example, for Chem, Bio, method specialist for both 11 and 12. One amazing resource is ATAR Notes Plus. Now, I graduated last year, and this is something that I used in the back half of the year because of the nature of methods as well. You want to be doing practice exams, and especially if your teacher isn't giving you so much, your teacher isn't writing the exam. It's it's QCEE that are writing the exam. What does that mean in practical terms? That means that your teacher can't predict what's going to be on the exam. But at ATAR Notes Plus, we have a comprehensive spread across the NEET practice exams. There's three for methods, and then Tech Free and Tech Active, and also the topic test. So my first point of call for the methods was to go through those and identify where I was weak, and then I cross-referenced and actually worked out what I needed to work on. Then I went on and did the practice exams, and they're of high quality. They are reasonably difficult, which is good when you want to test your understanding. Okay, so a bit of stuff about me. My name is Dash. I live up in far north Queensland. I'm a JCU so James Cook University first year medical student and on holidays right at this moment. Part of my journey through senior to get into medicine, that was my idea, my dream from about year 10, was I knew I had to get a competitive ATAR. So I got an ATAR 99.15, which I was just absolutely blown away with. And part of that was doing really well in methods. Bit of a side note, I love running. I've run an ultra marathon and a marathon. I'm currently training for another marathon. So I really enjoyed senior methods. I think it's very satisfying once you're at the end of methods and you have an altogether understanding. And for me, that translates to doing quite well. I got 97 out of 100 for the year. I think in year 11, I was mid low 80s, not anything close to that. So it really shows how if you put in the effort in year 12, you can really step it up and really do quite well. I didn't expect to do nearly so well. I dropped 1 mark on internals on the IA2. I forgot a plus C. As you recall from Unit 3, I forgot a plus C, and it actually wound up being the difference between a 14 or a 15, which was definitely quite annoying to be that close. However, I did really well in the externals. I got 48 out of 50, and that external was like from what my teacher said. The teachers all have this Facebook group where they talk about how hard the exam was, what are key things. Because obviously, you're all in this together, and they said categorically that this was the hardest paper. So last year's paper was the hardest methods paper that's ever been dished out. It was a really hard paper, and there was this. So the last question was this log question on paper one, and it was like prove that it equaled, and it like that this statement was true, and you had to like compare these two logs, substitution, elimination, and it just clicked through. And so far, I'm the only one I know who got that last question because it was really hard, but it was really satisfying. We had like this super complicated question, simplify, simplify, log laws, boom, proven. It was a really nice question actually to get. But that being said, especially the tech active paper, there were some really difficult questions that were on that paper. So it was a pretty hard paper. You benefited by doing specialists, but what I'm trying to say is methods is quite demanding. But if you do the work, as I definitely did, and are studying before that term 4 break, you will do well. You have my word that if you put in the work and are doing homework even now, you will do well. It's great to have a buffer where you've done well on your internals, but I'm promising you that even if you were perhaps slightly below par on your internals, if you put in the work, a couple of weeks of study for your externals, you will pass overall for the year. Okay, what are we going to talk about today? Today is actually quite firm in terms of it's like packed with content. We don't like in specialist. I really had to speed through because I had a discussion at the end where I was talking about, okay, what are some strategies for methods? Today is making sure that you know the intricate details of the content, and we are going to go through that today. So today's all unit 3, 4, sorry. Unit 3 was for the calculus, so logs, differentiation, applications, integration. We're not talking about that today. In fact, we're not really even talking about those first two, which is differentiation and application or trig. In unit 4, we're talking about probability, and probability is what makes up the basis of unit 4. It is statistics, and at times it can seem really boring, but statistics is high yield. Statistics is, in essence, pretty easy. If you understand the concepts and know how to differentiate between the different types, see those three there, you're going to do really well when it gets to your statistics on your exam. You're going to do exceptionally well, and you're going to be looking back and going, wow, I didn't even think I could go so well. What are we going to be talking about today? Discrete random variables, continuous random variables, and the normal distribution, then interval estimates for proportions, which are our confidence intervals. So yeah, here's an overview of what we're going to do for today. Bernoulli sequences and binomial distributions, continuous random variables, the normal distribution. In terms of the structure, today we've changed it up in past years. We're now going with 2 hours recorded lecture, so this isn't live, and that will be all content. So as you're watching this lecture, if you see something that's confusing or you don't understand, or perhaps it's a question about course structure, what services we have available, etc., there's a live chat. It's going right now. Feel free to just say hi. I'm wondering about this, and I'll be able to answer your question live. But we don't want to. We want to get 2 hours of pure content in. Hence, this is recorded, and the slides will be downloadable. So don't worry if you don't get everything in today. You will be able to go over the slides again before you start your external exam study. I'd spend an afternoon, an hour or two, just flicking through slides because obviously you've got 3 sets of lectures for our Headstart series, all for free, and you can download these slides for free. And you'll be able to just flick through them and just refresh yourself on all the content so that you're across it. You can do that before you start, your simple familiars, your complex unfamiliars. And what that's going to do is it's going to ensure that conceptually you're there. Conceptually you understand. Then it's the application. And to be honest, you should be doing weeks and weeks of practice exams. And I've said it before, I'll say it again. 800 Notes Plus, you sign up, you get topic tests, then you can back check your understanding with the summary notes, which is really nice because the summary notes have like written in a student's perspective. Really use them as a student. Like I really enjoyed them actually. And then you do the topic test just methodically, just go through them. Then you have the neat practice exams. That in itself is good revision. You will do well if you do all of those. Trust me. Go through those. Okay, cool. So statistics review. So just going to recap really briefly. Difference between discrete and continuous, expected value, variance, standard deviation, etc. What is a random variable? So, discrete random variables. The possible outcomes for these variables are discrete. What does that actually mean? They're separate and distinct. There is no spectrum or something like that. It is just set numbers, e.g., 1, 2, 3, 4, 5, and 6 on a dice. They're numbers. There's no like 1.25, etc. They're numbers. There's only so many we can get. Whereas continuous is actually an infinite scale, and more interesting things happen when we have continuous random variables. But I just wanted to define this here because we're going to go into different probability rules which we can use to determine the mean or the probability of something happening over something else, etc. And it depends whether it's discrete or continuous. Now, I will note that today, because we all have different calculators, I can't pull up my calculator and teach you how to use it with that because in all probability, most schools actually use different calculators. And although they have this similar underlying functions, you know, more going to be going over how to differentiate between which to use rather than what ones you will be using because it depends on the calculator. And I don't want to confuse you and say, oh, you've got to use norm CDF or whatever it is, when in fact it's something totally different for your calculator. Just something to note. And then, yeah, so continuous random variables, they're continuous. What does that actually mean? That means there are infinite little tiny increments for what it can be. And in fact, there aren't increments because we can go down to infinite detail, i.e., like height, distance, time, where like you could go to the bazillionth decimal point for a kilometer or further, or seconds, for example. And the crazy thing is, you are going to supersede all forms of measurement. We can't measure that far, and yet the measurement does go that far. And this is where we kind of get this concept of continuous. And like your height that you are right now, no one else in the entire world is that exact height because it's impossible to define that exact height essentially. Um, because it's like we can't measure that far because it goes on forever. It's infinity. And when we deal with continuous functions, what we can actually do is we can use integration to work it out. Whereas discrete, we use more binomial probability and stuff like that. Okay, so I'm going to go through some basic definitions, some basic values that you'll be using, some basic formulas, etc., that you'll be using for discrete data sets, and then I'll continue on continuous data sets and other ones. Now, one thing I will note is that if you see anything highlighted in red, what that means is you have to memorize that formula. And I know it'll be overwhelming right now because you're essentially learning a unit in 2 hours. And that's fine. What I recommend is you get out, go to your book right now, go to your book, get out your book and hold it up so that you've got that front cover, which is, made of a cardboard. And on the inside of that, on that like white space there or whatever it is, or perhaps just on a blank page, that would also work. Every time you see thing that red or, whatever, every time you see something that's in red, in black, etc., I want you to write it down. Now, the black ones, I will note, the black ones are not for you to memorize. And the reason I say that is that they are on the formula sheet. You do not need to memorize them. However, you should have an understanding of how they derive, what they actually mean when you use them, for when you're going to use them in questions, right? And that is what I'm essentially going to be going through today. We're going to work examples, answers, solutions, etc. Also, the red ones, though, these are things that you should know, and they're not explicitly on the formula sheet. So you should know them. Now, for our discrete data sets, these are what you would have gone over in year 10. You've already done these, which is good. So the expected value of a discrete random variable x is found by summing the products of each value of x and the probability of achieving that. Mathematically, we write this out as, the sum between x, the probability of x equals x. And what we essentially get is this formula here, which you can find on the stats page, which is like the second or third page. And you use these for all discrete data sets. So if we're talking about like dollars or, if we're talking about money, if we're talking about, anything where it's discrete and not like height or measurements, which have error and stuff like that, I want you to use this formula. And the formula itself is written in a confusing way, but essentially what you do is you just um, add each of the following terms, and each of the terms is the probability, P of I, times the value of X. So, for example, if it was like $10, we were like summing up all these different, probabilities of achieving a certain amount of winnings on at the casino or something. And one of the outcomes was $10. So it was roulette, who knows? And the probability of getting that was 50. We would do zero point 0.5 times 10. We would then add up all of the other possible outcomes, and that could be zero, for example. One thing to note, the probability should always add up to 1. Now, we denote the mean or expected value as the letter or the symbol there, which is U, and we call it as the mean of X. And that is also the same as expected value of X. So E of X is the same as the mean of X. They're both the same thing. They're both the same concept. We're just, writing it in a different way. And it doesn't matter which one you write on your exams ultimately, as long as you write one of them with your working out. Okay. Now for our continuous data sets. And as I said before, our continuous data sets have something slightly different going on. And that is that we're using integrals to work out the functions, because if it's a continuous function, what does that mean? That means that the graph has a shape. And if the graph has a shape, one interesting property that we find is that if we integrate, we can actually find the probability of it being between 2 points. So if we were trying to find the probability of, you know, so let's say we have heights of males or females, and we were trying to find the probability that the height of a random student selected will be between random student, random variable, what are we thinking? X. If we were trying to find the height, the chance that a random student selected was going to have a height between 1.6 and 1.8 meters. Well, if we were given a function that described this, we would integrate that function between 1.6 and 1.8 if it was in meters. And what we would find is actually the probability that we would actually find, you know, a student between those two sets. And it's a really interesting function. And then we get on properties is that they're integral between the maximum minimum bounds of the function, probability density function, is going to be 1. So when you're working out, if we're given a function, we can actually calculate the probability by integrating between 2 points, the 2 points that are given in a function. And in fact, if we look at the probability of one exact point, like 45.0222221116, whatever, that's going to be 0. And that's because it's continuous. At any given point, it's 0. But if we go on an interval, we will actually have a value for the probability, whether that's large or small. And so we can actually find the integral using this formula. And what we can do is actually determine the mean or the expected value of a function of x for a probability density function, where x is our random variable. And so this top formula is just showing you the derivation. And whenever we see a sum sign, often it translates to an integral. And what I want you to know, I haven't put it in black here, so that's my mistake. I didn't mean to change them all, but it is in red here. I'll just, if it says on the page that if it's in the data booklet on the stats page, that means you don't need to memorize it. But it's still worth writing down just so you have an understanding of where we're actually getting these from. And, just the header and then the formula, that's sufficient just for now so that you've got a bit of an understanding, right? And then you'll consolidate that when you do it in class, questions, revision, etc. You'll be building on this, building on it until you get to your exam, and then you'll be ready to ace that exam and do as well as you possibly can, because your potential in this external exam is going to be 100%. And you have to believe that, because I certainly believe that, and you have to believe it yourself. Otherwise, you will be limiting how well you can do your potential on these exams. So the formula for the mean or the expected value, once again, the mean is the expected value. It's kind of like the middle value. It's a measure of central tendency. We also talk about median, but we'll talk about that later. Don't worry about that for now. We're just going to be talking about mean, and mean is also known as E of x, or the expected value. Denoted by this symbol, it's called nu. Okay, so you can find this formula on the stats page in the data booklet. This formula, essentially, what we do is we integrate between the upper and lower bounds of the function, p of x being the function here, the probability density function, essentially. And when we integrate between these 2 points, we'll this is how we find the probability. However, to find the mean, we have to do this weird thing where we times it by x first. So p of x times x inside that integral in terms of d of x between the upper and lower bounds, which is often negative infinity and positive infinity. Sometimes we have multiple functions and then we break it up. This is going to be our formula, and you can find this in the data booklet. And you do get marks. There will be questions on that external that ask, hey, I want you, and on your internals as well, please find the mean or the expected value for this function. And by integrating between the upper and lower bounds and timesing it by x, as as per this formula, you're going to get marks for that, and you will do well in your exams. You're going to pass your exams by just writing formulas from the data booklet and answering them by subbing in values. So p of x is the function, nu is obviously mean, the expected value, and then we go from upper and lower value, just noting that we times it by x. That's what this formula is essentially saying, right? Okay, so this is the derivation of the expected value formula for continuous data sets. Now, you don't need to know this formula. I've put it here just for a bit of fun, and also, a little bit of an example, I guess. But you don't need to know it. For me, what I want you to know, like I got this here just to show. I know that there's super brainy maths people out there that are looking at this going, oh yeah, yeah, that's how it works. You don't need to know it. What I want you to know is that last line there, because that is in your data booklet. You should know when to apply that, which is if we've got a continuous data set, i.e. height, i.e., any kind of measurement, which isn't like a dollar value, it's a continuous data set. If you're asked to find the mean or the expected value, you are going to integrate between the lower and upper bound, whether that be negative infinity, positive infinity, or whatever, B and A. And what are you integrating? You're timesing x by the probability density function, by function of x, in, in terms of x. And that's in your data booklet, stats page, which is the second page of your data booklet. If you're ever in doubt in an exam, my recommendation is always to go straight to the data booklet, have a look, what are you actually dealing with, you know, have a look, and usually you can figure it out from there. It can be a bit mathsy and the terminology can be a bit weird, but as long as you've done enough practice questions, you should be able to work it out. And it is all labeled, and there's, although they don't tell you what's what, in terms of the variables inside of an equation on your formula sheet, what they do is they tell you, okay, you've got this is for this problem, this they've got titles, which will really help you to work out what you need to do. Okay, variance, discrete versus continuous. All right, two different formulas here. Once again, these are just on the formula sheet. Don't need to go through an example because all you're going to be doing is just subbing in values. Now, that being said, I will preface that with variance is a two-step thing. You'll get 2 marks for it. The reason being, you have to know the mean first. These formulas, what you'll notice is they actually involve nu. So this is the symbol nu. And what is nu? It's the expected value. It's the mean. So because we have to know the mean, you actually have to sub in the mean to this equation first. So for discrete, this is also in the data booklet. You don't have to memorize it. Worth writing down anyway. That's why I've put it in red as like, it's worth writing down and trying to understand when you would use it. So if we have a discrete variable, for example, dollars, probably the best example. Like we had different winnings that you can get from casino. Well, we are going to be using this formula, and the probability should all equal 1. That's part of this. That's a basic assumption that we've got here, right? All of our probabilities should add up and equal to 1. We don't care about what the x's are, but all of the probabilities, the p's, should equal 1. Now, what you'll notice, this discrete random formula, is similarly, so this is sigma, it means sum. Similarly, we're actually just adding up the probability times the x value. except we're doing two things. Number one, we're minusing the mean, and we're squaring it, which is interesting. You wonder why. And my explanation for why this is occurring is ultimately, if we're talking about the variance, we don't care where it is. Like if you picture it as a scale, we don't care where x is. What we care is how much this interval here is. It like we don't care if it's here or here, but whether it's big or small. And so what we want to do is, um, we want to add the mean in, because what we want to do is we want to see how much varies from the mean. We don't want to just talk about the x values, because that's not an accurate representation. We want to subtract away the mean so that we kind of like standardize them. We make them uniform. That's my explanation for this, and hopefully that helps you to understand. Um, but yeah, you'll notice that those are the only two changes. We're minusing the mean and then squaring it. So instead of just having the probability times x, and then we sum that up for all of the different values of x and their requisite probabilities. What we're going to do is we're actually going to minus the mean first and then square it. And this is on the data booklet. I do recommend writing it down just so you have a bit of an understanding. But yeah, whenever you see that sum symbol, if you're confused, all you do is you just sub in those values, and little I means that that's for one of them. For example, the probability of winning $10 at the casino is zero point 0.5. However, the probability of winning $1,000,000 is 0.001. You would have to then go all the way up to the $1,000,000 value and go, okay, the probability is 0.001 times $1,000,000, and you would just add them up sequentially. That's how you do the expected value. When we've got variance, what we do is that million is going to be minus by the mean, and the mean is going to be like what, $8 or something? We would minus out the $8 first and then square it. And that tells us what the variance is. Similarly, for continuous variables remembering anything like height, anything where it's a measurement, and that measurement has lots and lots and lots of little distinctions. What are we going to do? We are going to do this x minus the mean, but this time we're talking about it in terms of an integral. Once again, this formula is on your data booklet. So I haven't gone through an in-depth example here, but one thing to note again, you have to know the mean first. To work out, work out the variance, you need to know the mean. And so sometimes, you might have a three-step question where it's like, oh, determine the variance, or it's two steps, sorry, and you're going to have to do the mean first. Just remember that. Don't get freaked out when you look at the data booklet. Just go, oh, that new symbol, that little new symbol, that means mean. So what am I going to do? I'm just going to find the mean first using the formula in the data booklet. Another example where clear working out is absolutely fantastic, because you're going to be able to access those marks that are available to you much better. Okay, so the only difference here is that we're integrating. So in general, when we're calculating variance, it's kind of like x times um, probability, really. So it's kind of like the value times its probability. That's the general kind of like layout. Then we have little distinctions that are just on your formula sheet. For example, for variance, which is like how much it's varying. Once again, we have x, so the value of x that we're talking about that's given here for variance of x minus its mean squared times probability of x. So whatever this function is, so it's going to be this times the function of x, because remember, with continuous, it can be described by an equation. And equations are like f of x or p of x. We would times that equation times x minus mean squared. And once again, this formula is remarkably similar to what? To this formula, where we're timesing x by the probability density function, this guy here. And what are we going between? The upper and lower bounds. And once again, look here, it's between the upper and lower bounds. So you just simply work it out, you simplify what's in there, then you integrate it between negative infinity, positive infinity, which is something that you should be pretty confident with from Unit 3. And if this was tech active, you would just plug this into your calculator. Obviously, you can't put infinity and negative infinity into your calculator. So what do? You just go 9999, you just type in like 10 nines, and it's going to be ridiculously accurate. because these things, these probability density functions all have to approach zero anyway. So what you'll find is you're going to be accurate if you do that, even though, it's not technically infinity. It's approaching zero anyway, so at some point, it's pretty much accurate. So yeah, these are the formulas from the data booklet. Hopefully, I've given you enough time to write them down. Otherwise, like, ask questions in the live chat. I can drop links, screenshots, etc. I will be active 100% of the time, so just send me a message just on the live chat. And also, if you want more explanation or what you need to know, whatever it is, just let me know in the live chat. And I will note, this is what I meant to say. These slides are going to be available, not for when, that's not up to me. However, they will be made available and you will be able to copy off these. I would recommend 100% search them up on the website, go like July 2024 lecture series methods, go over these before you start revision and just like, it'll just refresh your brain because you haven't gone over these in so long, right? It's been so long since you've gone over these, and that's going to cause problems because you're not going to be confident on things. All right, standard deviation. This one, it's for both discrete and continuous. If you're asked for standard deviation, all you do is you um, do the square root of it. Now, this formula is not on the data booklet, and what that means is that you're going to actually have to memorize this one, unfortunately. Standard deviation is given by the letter or the formulation of, I'm not even sure what that's called. Maybe it's like omega or something, I'm not sure. But you have to memorize this formula to find the standard deviation because you're given the formula for variance between Bernoulli, discrete, continuous. You're given it for all three of those. However, you're not given the same deviation formula. And often questions, see how this can now be a three-part question that I've already shown you? Find the standard deviation for this data set, discrete or continuous. What you're going to have to do is, number one, you have to work out the mean. Number two is you have to work out the variance, then you have to square root it. Now, that can be extrapolated to a 4-mark question even if it's tech-free, because what you have to do is you have to do the integral, and that's worth a mark because there's room for error there as well. And you can already see how simple concepts can be extrapolated to a fair few marks, which, if you've learnt the content, are really going to help you pass. And you can definitely pass even if you're on, like, perhaps you feel like you're only standing on one leg at the moment, your internals haven't been great. This is the right time to pick up in terms of content. Even if you're failing right now, you can pass. I believe in you, and you should too. So therefore, we can say that the variance is equal to uh, this sorry, um, yeah, variance would be equal to the standard deviation squared, and that's just rearranging this formula. But definitely write this one down on your data booklet, and it's something that you're reviewing the night before and just trying to memorize. Okay, you should be memorizing it before the night before, obviously, but it's something that you definitely need to revisit, and is definitely worthwhile. Okay, what is a random variable? So a random variable is a value who's unknown. Its value is unknown, or it's even a function that assigns values to each of the experiment's outcomes, such as probability density functions. So it's used to quantify occurrences of a random occurrence, e.g., rolling a dice 3 times and finding the sum. The result is random. We don't affect that. That's not controlled. There's no factors that play into it. Or there is, but essentially we average it to be random. Obviously, the factors would be like forces involved and the texture of the surface and friction, all this. We just assume it's random. So it's different to an algebraic variable where the result is not random. So I just want to make sure that first sentence is right. If you have a probability density function, it's not random. Random means that we don't know, whereas a probability density function is an algebraic variable of value, right? The result is not going to be random. And we can classify these as both discrete or continuous. So discrete, once again, like dollars. What's the problem? Like going to the casino. Whereas continuous would be any kind of measurement where it's like height or distance or something like that. There's infinite little deviations that you can get, and no one thing has the same size exactly. We can lump them in the same like 1 centimeter, but there's going to be error either side of that. We don't actually know exactly in that band where it falls. And we're talking about bands, we're talking about continuous variables. Okay, Bernoulli sequences. So we've talked about discrete values. We've talked about continuous. We've talked about how to find the means, the standard deviations via the variances. And I've also described to you how you would find the probability for each of those. So for continuous, we integrate between the two values, whereas for discrete, it's actually given already what the probability is going to be. Sometimes you just have to do like it'll give you the probability of yes is 0.5, what's the probability of no, and it'll be like also 0.5, so 1 minus that. But usually it's kind of like what you did in year 10, kind of common sense as opposed to having to plug in values as it is for your continuous variables. Okay, Bernoulli sequences, number 3 on what we are going to talk about today. So Bernoulli sequences describes a sequence of repeated trials. And one thing to note is Bernoulli sequences are always success and failure. That is essentially what is going on here. We're talking about a success and a failure. And the probability of success is P. The probability of failure is 1 minus P, because there's only success and failure. And remember that the probability of all outcomes has to add up to 1. So what does that mean? That means that if the probability of success is 0.2, well, that means the probability of failure is 0.8, because there's only 2. Binomial, it's got to add up to 1. Okay, so I have 3 rules here, and I've said that you have to memorize them because you have to memorize these. These are 3 rules, and they're it's one of the little points where you actually can get marks for essentially just writing stuff. So if you memorize these 3 rules, there can be questions on an external exam where it's like write Bernoulli's sequence, the 3 assumptions, the 3 rules of Bernoulli sequences. Sometimes you might be asked which would be a Bernoulli sequence, and we're going to go into an example that is talking about that in a minute or two, because you could get this a multi-choice. I will note that the first 10 marks of that first paper is going to be multi-choice, and multi-choice can be difficult because if you make a little error, it's so easy to have, to pick, because they'll have the little errors translate to different questions, different options, A, B, C, D. And you might just go, oh, it must be D without checking, and you lose easy marks. Multi-choice is a place where, like, you need to, like, you can achieve easy marks. I would always drop, like, 1 mark even, maybe. I usually aim for 10, but sometimes you lost a mark because sometimes it can be a bit iffy. But this could be an example of a multi-choice question. And yeah, multi-choice, also make sure you write, like you can circle it on the booklet and cross out wrong answers. Make sure you follow it in the bubbles. At my school, in my year, in general maths, so not methods, there was, a student that didn't fill in the bubbles and automatic, and they were already in a poor shape, ended up failing the year because you need, like, if you don't fill in the bubbles, you're missing the simple, familiar, easy marks on the paper that they're ultimately trying to get you to pass with. Fill in the bubbles and just use a lead pencil so you can rub it out. Just do it early on in the exam once you've done it, and then you can come back and change it later. So the 3 rules I do want you to memorize. For me, this is a key learning objective. You need to memorize these 3 Bernoulli sequences. We can only have success and failure, number 1. Number 2, the probability of success, P, is constant for all trials. That's 2. Number 3, the trials are independent. Write these ones down. You need to memorize these 3. Okay, so here's an example, as I said, where we're going to actually test this in an actual scenario. So which of the following is a Bernoulli sequence? If you're rewatching this, you can pause it, have a go. If not, I'm going to go through them now. So the only one that I've classified as a Bernoulli sequence is A, B, could be, but, we're not, technically it's not. So A, we're tossing a fair coin a few times. So fair coin, that means the probability is the same. it doesn't matter what it's just landed on as to what it will show next time. So the trials are independent, and it's success and failure. It's either tails or heads. So by success and failure, we just mean one outcome or another. If there's just two outcomes, or we can classify it as just two outcomes, or lump them together so that it's just two outcomes, it is success failure. Binary, it's going to be a Bernoulli sequence. So A is a Bernoulli sequence. However, when we look at B, so trying to score a goal multiple times, this is unlikely to be independent. And the reason I say that is like if you've scored a goal, it's going to give you confidence, and you're probably going to be more likely to score a goal in the future. Like athletes who start doing well, more likely to then keep on going and do well. Also, the probability is not therefore going to be constant. Like you know, you're going to be tired by the end of it. The chance of scoring a goal might be higher or lower at the end, depending on your level of fatigue versus the goalkeepers. Hence, those last two, so independent trials, not true because if you've scored a lot of goals, you're probably more likely to keep scoring due to the morality, the psychology of that. Number two, also the probability of success is different. It's changing, it's fluctuating due to fatigue and stuff like that, more of this human kind of psychology type thing. So as you can see, as soon as there's a human element to it, unlikely to be a Bernoulli sequence. But then again, like if you had quiz results and they were random, I mean, if they've told you it satisfies the three, I'm happy. Okay, finally, we had selecting people at random from a high school grade and noting their age. This is not success and failure, unless we specified and we said, and noting whether their age was 20 or not 20, but like 12. That would then be success failure. But the way this is worded, selecting people at random and noting their age, uh, sure, probability of their age might be random. However, and trials, sure, probably independent, but there's not success failure here. So C is not a Bernoulli sequence. Okay, a bit more on Bernoulli sequences. So Bernoulli sequences are typically, or they are discrete random variables, and that's because it's success or failure. It's a discrete outcome. It's either going to be success or it's going to be failure. And often we use Bernoulli sequences to kind of like extrapolate some probability questions for some of our discrete variables, as I'm sure you're going to see in your class, and also we're going to go over some. So the outcomes from a Bernoulli trial and sequence can be represented by Bernoulli random variable. We can set it up, table like this. This is just a nice 2 by 2. Y, we have failure and success, and then the probability that Y or X equals that is defined there. So one take P for failure, P is success. Now, I've defined from memory, there's a couple of key steps for a Bernoulli sequence question. Uh, and these ones are pretty universal. So I reckon this is worth writing down as well. First of all, and I will note more broadly in a more meta sense, if you can write out the steps for answering questions generally, like go through the objectives, what steps are there to answer those generic questions? You can find the objectives by Googling methods 3-4 syllabus, QCEE, and go through that until you find them. What number, if you can write the steps out for each objective, you're going to do really well because you've now got a really nice conceptual understanding. And that's going to make your application oh so much better, right? It's going to really help you differentiate these different types of probability because right now it's difficult because you're like, it's all blending together. However, once you've differentiated them clearly, for example, the typical things for a Bernoulli sequence, you know it's that, and you use that formula from your data booklet that we're going to go over. When you see success, failure, etc., when you see that, you know you've got to go over Bernoulli sequences. Okay, so the steps to answering a Bernoulli sequence question. Number one, identify. Does it meet the three criteria that I just said on the other page? And that's going to tell you you're going to be using the formulas from the data book, which we're going to go over. Don't worry. So number two, define one of the outcomes as success, which is X. Then you want to fill in other values from the data booklet, and for example, the probability of X, like what's the value of X we're talking about, and because what we're going to be doing essentially is filling in there's this formula on the data booklet labeled Bernoulli sequences, and you're just going to be filling in the number, the probability, and then working it out. And sometimes we have to do a bit stuff that's a bit more complicated for that, as I will show you. So this is the formula in the stats page. This weird thing here is what I'm going to go over now, because the rest you can just sub in the value of x, the probability that x equals x. So this is kind of talking about like the number. So if we have, so I'm going to explain this in simple terms when you use this formula. Question asks, what is the probability that we're going to have? So we have, you're rolling the dice 6 times. What is the probability that you're going to get? So the probability of success would be 1/6. What is the probability that you're going to roll 2 6s if you roll the dice 6 times? And so what you're going to do is whenever you see a 2 here, you're going to sub in 6 for 6 trials. X would be 2. So we're finding the probability that X, which is the number of that, equals 2. So 2 success outcomes. We define success as getting a 6. Probability would be 1/6. So 1/6 to the power of 2 times 1/6 to the power of 2. And this here is called a combinatorics. I'm going to show you that. Don't worry. It's that. But now we would find, and this formula just allows us to work out what the probability of actually getting that number of sixes would be. That's for your Bernoulli sequences. So you would define, so identify, is it a Bernoulli sequence? Yes. Define one of the outcomes of success. Then you fill in these values. For example, the number of trials n, for example, x, the number we're interested in, and the probability of x as well. Okay, so Bernoulli sequences, combinatorics, you should have learnt this in year 10, but different schools are different. We use this formula, and this isn't given on the data booklet, which is quite frustrating. I know for my calculator, if you just typed in NCR bracket the n comma r, it'll tell you. But r is the x value, essentially. It's the value of x there that we're looking for. It's like the actual value that we want, right? Whereas n is the total number of trials. And it's just multiplied out the front to this formula, which is kind of annoying. But as you see in questions, it's, you eventually get used to it. The way to think about it for the order is n chose r. And the reason I say that is we can use Pascal's triangle to calculate these combinations tech-free in methods. You're going to have to Google how to do it tech active because I don't know what your calculator is. For me, it was just NCR bracket, whatever, whatever. But just look at a YouTube video. It really does help. Okay, so you have to memorize Pascal's triangle. This is universal for your tech-free questions. And what happens is we've actually got these values here. So you go 1, 1, 1, 1, 1. One's always on the outside. And you go in these different rows. This row would be 0. This row would be 1, 2, 3, 4, 5, etc. N goes down, R goes across. R being the number we're interested in, the X value gives specificity. And what you'll see is when you're drawing this, so have a go at drawing this. 1, 1, 1. This 2, well, I'm not just making this up. This comes because 1 plus 1 is 2. Then we put 1s on the outside. Now, if we go 1 on the outside, 1 plus 2 is 3. 2 plus 1 is 3. 1. Then here, 1's on the outside. Just adding 1 each time because it's like a triangle. 1 plus 3 is 4. And 3 plus 3 is 6. 3 plus 1 is 4. And then we put a 1 on the outside. And we just keep going down and down and down into perpetuity. And you do need to memorize this, or at least how to work it out. For example, if we had like n equals 5, r equals 2, well, we would go down to 1, 2, 3, 4, 5. This would be 1, 2, would be 4. So the value of this thing here would be 4. We would sub in 4 to that equation to then work out the probability that we get that number of successes in that many trials. Okay, cool. Now, there's a couple that you do need to just straight away memorize, unfortunately, and that is the NC0. So when r equals 0 is 1, NC1 equals n, NCn equals 1. So just write those on your formula sheet. If you ever get a question like that, It's nice and easy. You don't have to do Pascal's triangle. You could, of course, do Pascal's triangle. You get the same, but I would just memorize these really quickly as well. But yeah, these ones are to memorize. These are not on your formula sheet. Okay, so this would be an example. It is actually the example I made up just now. So obviously my memory recalled it. So Bernoulli sequences, consider rolling a die 3 times and letting x be the number of threes represented. Well, the probability that x equals 3 is going to be, if we extrapolate it, what are we going to get? I'm just showing the derivation of the formula here. What we would do is, we would let success, which would be t, equal 3. N would be not a 3. We could also let x equal success, so equals 3. And the probability that x equals 3 is 1/6 to the power of 3 of getting TTT. And this is just using like our tree diagrams, something that you learnt back in, you know, year 10. There's different combinations of TTN, etc. And I don't want you to know these. This isn't typical for me. What I want you to know is to know these 3 steps, and then and then apply them. Sub it in to this formula, which you might have to use that for if it's tech free. So this is the different combinatorics we would use. So when x equals 3, we'd use, because the trials are still 3, right? There's still n equals 3, but the value of r, or the value of x, is going to change. So when x equals 3, it would then be 3c3 for NCR. When x equals 2, it'd be 3c2, x equals 1, 3c1, when x equals 0, it'd be 3c0, 3c0, etc. And we get these different probabilities that should all hopefully add up to 1. Okay, so we'll do an example now. Find the probability of obtaining 3 heads when a coin is tossed 6 times correct to 3 decimal places. Pretty classic question. This is just be simple familiar. So it's only heads or tails, so already we know that it is going to be a Bernoulli sequence. And probability is the same, independent trials, etc. Now, we're going to let success equal heads, and we're going to let x equal the number of heads we're going to observe, where the probability is 0.5, probability of 6 is 0.5, r equals 3, and the number of trials equals 6. So the probability that x equals 3, now we just apply the formula in the formula sheet. And what we get is this combinatorics at the front where n equals 6 and r equals 3. Now, if we go back to our permutation, you could use a calculator, of course, but n equals 6, so 1, 2, 3, 4, 5, 6, 3, 1, 3, and we find that that's equal to 10. And that would just be a scalar multiple of these two values here. And look, at the end, you get 5 over 16, and that's the probability that we would get 3 heads when we toss the coin 6 times. So fairly likely, considering all the outcomes we got right. One thing, like, see that logic I just used then? That's checking your reasonableness. And after you've done a question, you should always look at it and go, okay, is it reasonable? And there's basic levels like, oh, is the probability between 0 and 1? Okay, that means that, yeah, it's probably fairly reasonable. Or if it's crazy high or crazy low, you might go, why is this? Is this reasonable? Okay, so a Bernoulli random variable describes the outcome from a Bernoulli trial. So if x is the number of successes in n number of Bernoulli trials, each with the probability of success of p, that means we've got a binomial probability distribution. So we can actually graph this and, the probability and outcomes of x. So binomial distributions we represent like this. The binomial probability distribution is different for values of n and p. If we change n, if we change p, it's going to affect the value, of p of x equals x that we get. So an example here would be probability of guessing MCQ questions with success rates of 0.2 versus 0.5. So when so this is like the number of outcomes that we get versus the different, probabilities. And the probability of obtaining that number of outcomes successfully guessed is different depending on the probabilities. For example, in the first one, when the probability is only zero point 0.2, so if you're guessing those MCQs, you're only getting four or six right? Between 2 and 6 really. Whereas if your probability of getting it right is zero point 0.5, so it's true false, as you can see, the binomial distribution is centered around 10. The mean is 10. That's the highest point. That's the mean. And it's kind of even as well. I'll note that that's even. And the probability of zero point 0.5 corresponds with 10 there. And, you're probably passing about 50% of the time by guessing if the guess rate was zero point 0.5. But unfortunately for you guys, that's not the case. Okay, so expected value and variance for binomial random variables. So if x is the number of successes in n trials, each with a probability of success p, then the expected value and variance of x are given by these two formulas. And I've forgotten to highlight these. You need to remember how to use it, but you can just get it straight from the data booklet. I will note you do not need to know how to derive these or memorize these. These are not memorized. These are on the data booklet. So if we're talking about a binomial, bi means two, success and failure, Bernoulli trials. These words all interlinked. And that should be your thought pattern. If we're talking about that, you're going to go to the data booklet, you're going to go to binomial random trials, Bernoulli or whatever it is, on the stats page, page 2, I believe, and you're going to apply these formulas. So E of x is the expected value, so the mean of x, n times p. So really simple. It's like in this question here, it's like the mean would be 10 and we have 20 trials. The probability of getting right is 0.5. So 20 times 0.5 is 10. That's the expected value. You can see how this all kind of works out and makes sense, essentially. Then the variance of x, a little bit more complicated, np times 1 take p. Yeah. So you just apply them, and remember, how do we work out standard deviation? If we were given that variance, how do we work out the standard deviation? We square root it. That's the standard deviation. As I said before, something you do have to have memorized. Example. So a test has 50 MCQs, multi-choice questions. Each question has 4 possible answers. A student guesses the answer to all questions. So let x equal the number of correct answers. So success is correct. X is the number of successes, and it is a Bernoulli sequence. That's step 1 we were supposed to do because there's success, failure, independent trials, and also its probability is constant. It's not changing, essentially. So how many would be expected to get right? Well, we're just going to apply the formulas that we got from the data booklet. And here, I've applied it here, I've highlighted it here on the stats page. N times P, 50 times a quarter. Similarly, for variance, we just sub in N and P to that formula. And what we get is 75 over it. And you're thinking, oh, that's more than one. Well, it can be more than one because we're talking about the variance of x now as opposed to the the expected value. Well, I mean, they can all be above 1. If you're talking about probability between 0 and 1. Sorry. Okay, so sometimes we want to find out, sometimes we want to find the sample size. And like I've shown you the basics now, you've now been shown the basics, but sometimes you have to go the other way. Sometimes you're given a probability of something, or they say, try and find the probability of finding this. And then you have to backtrack to find the sample size we need to get that probability to actually work, given the probability, etc., to observe a certain outcome. So an example would be, if we had how many lotto tickets would we need to buy to ensure a 95% probability of winning? And if you were just given this question, by the way, you would not be able to answer it. That is not something you would have to answer. The reason for that is because, yeah, you're given P of x equals 0.95. However, and you're trying to find n. However, we haven't been given what? We haven't been given r or um, or well, actually, yeah, we have been given R. We haven't been given the probability of winning on a single lotto ticket because R would equal 1 because we only need to win once. R would be 1 up to N, and N would be equal to, that's what we're trying to find. and then P of X equals R would equal 0.95, as you're going to see here. So yeah, the information we need is the probability of scoring equals 0.48. And here would be some example. So this is an example question I show you, but here is for goals. So before we were talking about lotto tickets, but here we'll talk about goals. So what is the least number of shots that must be played to ensure that the probability of winning at least once is more than 0.95, or at least twice is more than 0.95? And for question one, this would be how you would work it out. So using our binomial sequences, the probability that we're going to get, the probability is more than 95 of getting at least one, well, we would write that like probability of x greater or equal to 1 is greater than 0.95. And as soon as you write that sentence, this question becomes really clear because now we can work it out mathematically. Before it was super vague and, we can't actually work that out. So what I want you to know is if it's binomial, you should always, and we're asking for sample size or probability, etc., always state what you know. State what you know, and eventually it'll click through in your mind. You'll know what to do. And this, in terms of math, sometimes it's not this way, and you can have a fair bit more confusion. But at least here, it's nice and simple in that it kind of links in from one thing to the other. It's very sequential. Hence, you can't skip steps, but you can just work through it, and it does make sense. It's small logical leaps from next thing to the other. Hence, it's not complex, unfamiliar, really. Okay, when you combine distributions, that's when it becomes complex, unfamiliar, and you'll find complex, unfamiliar questions for that in your textbook. So, all right, probability that x is greater or equal to 1, we want to find when that is greater to 0.95. Well, I've skipped a couple of steps here, but essentially, greater or equal to 1 means that it's the inverse of x equals 0. Because we're talking about 1, 2, 3, 4, etc., all the way up to n. So what we're going to do, because it has to be a discrete value, we can't use these greater equal than signs in the actual probability. That's not going to work out. We're not going to be able to get a number. But if we do one take the probability that x equals 0 and we sub it in, so we have p equals 0.448, r equals 0, what we're going to, and then n is what's unknown. If we work that out, what we're going to get ultimately is 1 take 0.52 to the power of n. Then we minus 1 from both sides, get rid of that negative, and what we'll get is 0.052 to the power of n is less than 0.05. And right now this is like, what the heck, this is still confusing. But if we take the natural log of both sides, what we get is a mathematical expression that can actually be simplified. So if we divide out the logs, then what we get is that n, if we work it out properly, we'll get a mathematical result with this, right? We'll be able to use our calculators and work this out. And if it was tech-free, we would just leave it as such. You could also, like, I know in year 12, I wasn't using these equality signs like the greater or less than. I was just using equals, and then I would work out in my head, okay, so what's the minimum limit here? And then I would then put the equality in at the end. And that's totally fine. That's all good by me. If you are using equalities, the one thing to look out for is sometimes you've got to flip it. So you'll see in step 2 here, I flipped it, and that's because I've minus 1 from both sides. That's why it's 0.405 on the left. Now, that would mean I've got a negative on both sides, so I divide out the negative. And if you divide by a negative, that means you have to swap both sides. Divide by a multiplier, a negative, it doesn't matter. You have to swap both sides. Okay, part 2. So part 2 was asking, okay, at least twice. So the probability of scoring a goal at least twice being more than 95%. So once again, all we have to do is just set it up as a function. So we're trying to find the probability that x is going to be greater or equal to 2. And that probability is going to be greater than 0.95. Now, another way of writing that is that the probability of x being less than 2 is less than 0.05. Okay. And if the probability of x being less than 2 is less than 0.05, well, what are the two discrete values we have when x is less than 2? Well, it can't be 2. It's just x equals 1 and x equals 0. So what we do is we just add up the probability of x equals 0 and x equals 1. Here I've got the two expressions. This is using the the formula for binomial distribution. I've gone over it before. It is just in your data booklet, so you can just apply this one. Nice and easy. So you sub that in, work out the combinatorics using your calculator, etc. Sub these in, work it out. We get this value of n. Now, this is not solvable, FYI. This, because we got n over here and n here and n here, this is not solvable. Algebraically, not solvable. You need to use like a weird Gaussian limit. It was like it's essentially obscure maths that isn't algebraically solvable. So what that means is you have to use nsolve. And if you're like, what the heck is nsolve? It basically just automatically solves any expression. It's really good. Use it and abuse it in your exams, methods, specials, whatever it is. Use it and abuse it. Essentially, it just automatically solves the question. You just type in the expression, and then go like comma, what will you want, and a bound potentially. And this is the calculator I have. But it's probably in a different one for your calculator potentially. So what I want you to do is search up YouTube tutorial for numerical solve. That's what the end solve is, numerical solve. And it'll give you a short YouTube clip. It'll be like a minute long. Just tap through that because it is a life changer. It makes tech active papers actually much easier than tech free because you can skip so many steps. I remember in year 11 we had a tech active question where if you try, like, people spent half an hour trying to solve this question. It was actually unsolvable and it was only worth 1 mark for applying the nsolve function. Like, this is in marking guides. You need to know this. This is really high yield. Nsolve. No. Or numerical solve, whatever it is in your calculator. Solve any expression tech free automatically. And sometimes there's multiple, but you'll see that in a good YouTube video. Okay. So these were the binomial. We've now gone over Bernoulli and binomial functions for random variables. We're now going to talk about continuous random variables. So what are they? Continuous random variables are any variable that can take up any value in an interval with a real number line. So an example would be like the time to eat a whole pizza. Answers can be 1 second, unlikely but possible. 1.01, 1.00023, etc. Now, the thing I want you to note there is kind of reinforcing what we were talking about before, which is that's a continuous data set, isn't it? Because you can't write that all on a page. There is no limit to what numbers we can have. We can have it down to infinite levels of detail in any direction we want. It can be 1, etc., etc. Like, we can have any decimal value that goes up to numbers science can't even, like, it would take billions of years to just write the number down, and we still have more detail from that. It goes on to infinite detail, hence it's continuous. So any kind of measurement, the time, distance, etc., we're thinking continuous here, okay? And that's a key concept that I really do want you to appreciate, because otherwise you will run into trouble when you're trying to answer these questions. Okay. So we need a way to represent this data so we can actually work out the probability of different values occurring, because that's what we're doing, right? Stats, we're trying to find probability. We're also observing different things like sample size, mean, etc. Now, we need a way to represent this data so we can use probability distributions for continuous random variables, such as weight, such as temperature, such as distance, such as speed, etc. So this whole, for the last half an hour or so, this previous content block that I've been talking through was discrete random variables. And examples of that included like counting the number of people in a room or rolling a number on a die. We can't get these decimal places. And as soon as you think there's decimals, you should be suspicious that it's continuous random variable. However, it's something like money. We don't consider anything besides to 2 decimal places. That's just money. That's cents. Hence, it would still be discrete despite having decimals. But as a general rule of thumb, if you see decimals, if I were you, I would be suspicious that this is some kind of discrete um, random variable, continuous random variable. Sorry. So rolling a die, number in a die, number of people in a room, many variables aren't like this. Those are discrete, but a lot of variables actually fall under the continuous kind of rule. And for that, we need different rules for our continuous random variable data sets. And that's what we're going to go and now have a look at in this next section. In fact, there's different levels of accuracy that we talk about in continuous variables. So one key thing to note is that the probability that we have an exact random variable that is continuous, that is going to be zero. That value is actually zero. We can't actually work that out at all. Like that is zero. The probability that x equals one specific value is zero. It's only when we have an interval that we can actually determine probability. That's one thing to note. But yeah, so we're going to let h be a random variable with values being a person's height, so height being h in centimeters. Remembering that units is very important. Make sure you have units. You will miss out on marks if you don't have units. Measured to the n or the ith decimal place. So if we have h0 equals 175, what we have is actually levels of accuracy. We're not talking about confidence intervals yet. What this is talking about is actually like the measurement error which you would get on, say, a scale. So if you do biology, chem, physics, if you're doing your accuracy, sorry, your reliability correctly, that means that you're going to have error for each measurement. And that means that each measurement you do is going to have error, and you should be incorporating that into your calculations because your uncertainties could be incorporating your measurement error and accuracy. And it can definitely be a pain to work those out sometimes, as I recall. However, working those out is scientifically gold standard. You should be doing that. Now, similarly in maths, we don't call it uncertainty, but we actually do have a certain level of uncertainty. So if I say my height is 193 centimeters, that means that I'm not actually talking about 193 centimeters. What I'm talking about is my height is between 192 and a half centimeters and 193.5 centimeters. Because if I was below 192.5, I would go down to 192 due to rounding. If I was above or equal to 192.5, what does that mean? That means that I'm going to say 193. Similarly, if I'm up to 193.49999, I'm going to say I'm 193. However, if I'm above or I'm at 193, I'm going to say I'm 194. So you can see that when I say I'm 193, I'm almost saying it like it's a discrete measurement. But the truth is, nothing could be further than the truth. Like nothing could be further than the truth there. This is not a discrete measurement. It's actually a range of probability, and it's actually equal to half of the most accurate measurement. So if I'm measuring in centimeters, half of the most accurate measurement is going to be half a centimeter either side. Conversely, if we had, for example, millimeters, well, I would do like 0.05 millimeters. Oh no, zero point 0.5 millimeters. For example, it's going to depend on what that is. So the answer can never be exact, and it's actually dependent on the instrument used, the level of accuracy there, and you get more accuracy with like electron microscope versus a measuring tape, or measuring tape with like millimeters versus a centimeter ruler. So this is something to keep in mind, and it forms the basis of understanding that when we're talking about continuous random variables, we're often talking about these little intervals, and you know, and working out what the probability that they are between that. So even though it might be listed as a discrete variable, it's often a continuous variable because the measurement itself is continuous. It's just our measurement is discrete. Okay, so elaborating on this now is that random variable h cannot be an exact value. The probability that h equals h is 0. If we have an exact value, so that if I was to ask you, like as a trick question, what is the probability that x equals 100, that I'm 193 centimeters? You might go, well, you just told me, so it's 1. I'm not 193 centimeters. I am, and I don't know how much, and we can never work out how much, even with an electron density microscope or whatever. We can never know my exact height down to the infinite decimal place. Hence, if I ask you to find the probability that x equals h for a continuous random variable, such as height, any kind of measurement, I want you to say it equals 0. For all values of h, if it's directly equals h, it's going to be 0. There is not an exact value that we can use here that is going to be relevant. So we can only work within little intervals, such as on this graph here. This graph has little intervals. Each one of these bars is an interval between one to the other. And the reason that we actually have these bars have a height, because height here would indicate the probability. On the axis here we would have probability. This is the different values of x. The only reason these points, these bars actually have value is because they have width. If they didn't have width, they would be nothing. If they have to have width, because that's an interval, and then therefore they have a value of probability, which would be on the what axis? The y-axis. Okay. So, for example, if I asked you, a person at a height of 175.2, we're measuring to millimeters there, the 0.2, that's millimeters. That is going to be equal to the probability that they're between 175.15. So if I was asking for the probability that the height's going to be that, I want you to rephrase that in terms of the probability that it's between 175.15 to 175.25. Now, one thing to note is that we don't need a less than or equal to or greater than or equal to sign here, or greater than or equal to here, and a less than or equal to here for h, because the probability that h equals 175.15, likewise, it's just going to be 0 according to this rule here, this golden rule. If we're talking about continuous, the probability of it being one single point is 0. It's only when we talk in terms of intervals that actually has a value. So from this histogram, if we look at the probability that h1 equals 175.12, that would be here. We actually find the area of this histogram. We actually kind of simplify it to a discrete variable. We actually go, okay, you know that random formula we had before? It was like the probability of x times x. Well, that's kind of area, isn't it? It's length times width. And what's the length going to be? That's going to be x. The width is going to be, so the height is then going to be what? Probability. And then that tells us the total. So the probability that h1 equals 175.2, and the shaded area there. If we work out that shaded area, that's going to tell us obviously it's going to be greater than 1 because it's the probability times that. But if we divide that by the total area, it should be 1. That's going to tell us, or no, it won't be 1, but you'll have to add it up, unfortunately. Or it could be 1, not sure. Depends on the histogram, you'd have to have a look. But it will make intrinsic sense when you see it. That's going to tell us the probability. And you can get questions like this, and the key is not to overthink it. Do what makes sense, and you will do well. You have my guarantee. Okay, so as the intervals that we're talking about get smaller and smaller, we can actually use a nice and smooth curve to describe this entire function, like this. We can use a curve. If it gets smaller, this is kind of like one of the central theorems of calculus, is if the intervals get small enough, we can actually use a nice and smooth curve to describe it. Then what do we get? Well, this cumulative, what we get is it's a continuous, so we get probability density functions that describe these continuous random variables. And we call this probability density functions, which is also known as PDF. Then the probability of interest, is represented by the area under the curve between those 2 points. So using the example before, we were looking for a height of 175.2. We would integrate whatever the function is, so f of h, whatever the function is, between 175.15 to 172, so 175.25. And then remember that we've also always got to have this dh, which means, but in simple English, we're looking for in terms of h. So we would integrate between these 2 points in terms of h um, of this function. And this function, f of h, equals the probability density function. We call f of h there the probability density function. And this should start to look a bit familiar to the formulas I was talking about before when we were talking about our cumulative density function, when we were timesing x by it to give us, our mean, or when we were finding our variance. This should now start to look familiar because these concepts are all interlinked. And as soon as we're talking continuous, we're talking about a smooth curve. And what's one thing we can do with a smooth curve? We can find the area under that curve by integrating between 2 points. And if I'm telling you that the probability is equal to the area under the curve, well, what are you going to do? You're going to integrate between the 2 points to find the probability. And if you have a calculator on you, if it's a tech active exam, that is, what you can do is you can integrate between 2 points to find the requisite probability that you are looking for. Alternatively, you might get these questions where you have a histogram and then you just find the area of that histogram and then divide it by the total area under that curve. Okay, so we're now going to go through a nice example. So consider the following function, and you'll note this probability density function is I can't remember the word. It's actually frustrating me. If where you've got two different functions that determine it. It's not just one single clean function. We've got a piecewise function. Piecewise function. What you learn in year 11 is applying here. This is a type of piecewise function. And its function is, okay, so we've got f of x equals 1.5 times 1 take x squared if it's between 0 and 1. But if x is greater than 1, well, what's going to happen is it's going to be 0. So the probability is going to be 0. So when I say f of x, I'm talking about the probability there. So question 1, it's asking you to sketch the graph of f of x. Next, it's asking you to show that f is a probability density function. We're going to go over the rules that define whether something is or isn't a probability density function, because indeed there are certain rules where if it shows this characteristic, yes, it is. If it doesn't, well, no, it's not going to be. Then I'm going to ask you to find the probability that x is greater than 0.5 on this graph, and we're going to go through that and apply what I've just been talking about to that graph. Where the random variable x has the probability density function of f, which is just that f of x piecewise function up there. Okay, so I've used Desmos just to graph it. You can use your calculator, of course. But if you have to use a graph in your answer, you have to actually physically draw the graph. In fact, if you used, so a key rule here is, let's say the question was asking you to find a max point. This could be for unit 3 too. Well, that means that even though you just use your calculator, that question is going to have like 3 marks awarded to it because you have to pull it up on your calculator, use interpret graph to like find the max point, analyze graph, sorry. Then what you're going to have to do is you're actually going to have to draw the graph and identify the max point, and you say, oh, using this function, I found this. You always have to graph it if you use your calculator because you have to show working out, right? Otherwise, you could be cheating for all they know. Obviously, that's not what we want. So, first of all, you graph it, and that's what it looks like. So it almost looks logarithmic going down. Check the two conditions. So there's two conditions, two rules that you have to memorize for whether, so this is something to memorize, for whether it is a probability density function or PDF. So number one, the probability is always greater or equal to 0. So f of x is always greater or equal to 0. Here we can see it is because f of x does not go below 0. It never goes negative, because that would make, how do we have negative probability? Number two, the sum of all probabilities is 1. Now, usually if we had like a discrete variable, what would we do? Well, we would just add up all of the little probabilities for all the different x values, would equal 1. However, with this, what we do is we integrate between negative infinity and positive infinity, and we see whether the total area under all of the curve equals 1. Now here, what we have to do is we have to check that. And if we integrate between infinity and between negative infinity and 0, we're not going to have anything because the function is actually at 0 there. So we're not actually going to have any value there. Same ditto for between 1 and infinity. It's always going to be 0. So we're only interested in the lower and upper bound here, which is between 0 and 1, where this function is actually greater than 0. So we integrate between 0 and 1 of 1.5 times 1.5, 1.5 times 1 take x squared dx equals 1. And you'll find that that integral does indeed equal 1. And it's not too difficult of an integral to do either. If you are caught up on your integrals, as you can see, we're applying integrals here. You need to know your integrals. Also, you need to memorize that. So in the last couple of slides, you've had a bit of a break. Haven't been any memorized stuff, just application and understanding. This, you need to write this on your data booklet. You need to have written this down, for example, inside of your front cover, whatever it is. You need to have memorized this one as well. Check those two conditions. You will get, potentially, in an external exam, questions that are worded like this. So you need to know this stuff, right? Finally, we asked to find the probability that x is greater than 0.5. So what's the probability that x is between 0.5 and infinity? But we don't care about infinity. What we care is where it goes to 1, because from there equals 0. So we don't care about it. For this, so what we do is the probability of x being greater than 0.5 equals the integral between 0.5 and 1 of the probability density functions. This is what I was talking about before. This is an example question of that, and you can plug this straight into your calculator. Alternatively, you have to integrate it and actually work it out, which can be a little bit annoying. However, you might get an extra mark for that if that's tech-free, right? So these questions, altogether, not too difficult, but they can have some complexity at the same time. Okay, now we're looking for the mean and median of a continuous random variable. So as I said before, the mean is actually just equal to the lower and upper bounds of x times f of x, and this, and then variance is the same, except instead of having x there, we have x take nu for mean squared times the function of x, the probability density function. And what you'll notice is this should look fairly familiar. This is for a cumulative density function, sorry, not a cumulative, continuous density function, sorry, continuous random variables. This is what I was talking about before when I said, oh, this is how we calculate the mean. This formula is once again stated here. We're now reinforcing it on this slide. However, you don't know the median and you don't know the percentile. So one thing I will get you to memorize, one thing I will get you to write down are these two formulas here. So a median is another measure of central tendency being what actually is the middle. If we're trying to find the middle, we can actually go, okay, we can go mean, which is like the average, but median is actually just like, if we arrange all the numbers in order, it's n divided by 2 minus 1. And so we can actually solve for the median. Often you are asked to by integrating, because we're talking about continuous random variables using probability density functions, we can integrate between the lower bound, negative infinity, and m. M is what we define as the median. And how this works is we let the other side of the equation equal half, because we know that the probability that that x value is going to be less than m is going to be half. You can also go from m to infinity, or the upper bound equals half. So you do have to memorize this. If you see median, what you're going to do is you're going to say, let median equal m. Then you're going to write down this formula. You're going to sub in the probability density function, and then you're going to solve for f of x. Now, you can use nsolve to solve these questions. Here's something I will note. You can actually use them. You can use nsolve here. One thing you can't use, or you can also work it out manually using tech3, and you may have to do that in the exam, I will note. Now, this one, percentile is less high yield in terms of memorization. I'd write it down anyway, but basically tells us the percentile of the population. So write down this formula, Q percentile, but, and then we just sub in Q when it's given. Example, the best way to learn this one would probably be example, to be honest. Example, the 75th percentile is the value of P found by letting Q 75% equal 0.75. So if we sub in Q equals 0.75 here, we can solve for B, which tells us the percentile. Not asked the super a lot. We'll see IQR in a moment, which is high yield, but you definitely need to know the median of practice questions for that as well. Okay, so we're now going to go over another example. So, for example, we've got a probability density function. This probability density function follows the rule half x on between 0 and 2, and we're trying to show that this is a probability density function in question 1, and then it's 0 elsewhere. So, firstly, find the mean. Well, first we have to check the statement is true, so remembering our two rules. First of all, it's never less than 0, and also, so make sure you write that, and also integral between the upper and lower bounds, 0 and 2, where it's actually relevant, it's not 0. If we integrate that in terms of x between 0 and 2, that equals 1. Therefore, it is a probability density function. Question 2 asks us to find the mean. Now, the mean, what we have to do is according to the formula book, so don't worry about it, just go straight to the formula book. What you'll do is you'll find that we have to multiply it by x and integrate it between 0 and 2. So that, yep, here's the formula here. So between a and b, x times f of x dx 0 to x times half dx equals 4/3. Perfect. Question 3, we now have to use the median. So let m equal the median would be the first line of working. Now we just put in, you'll get a mark for this, for just stating that between negative infinity and m, the probability of that is going to be half. Now what we do is we solve for m, so you would have to have more expanded working. I've just used tech3 working here, which would be, if we were to plug this into nsolve, we would find that m equals square root 2. Whereas if you worked it out manually, you'd have to, work out the functions and manually integrate it, which is fine. You do have the ability to do that. Measures of spread. So we were talking about central tendency. Now we're talking about measures of spread. So left, right is doesn't matter, but it matters how big it is. So there's two common measures of spread. Number 1 is variance and standard deviation. Number 2 is interquartile range. They both have the same mean and median, but they are completely different. So standard deviations in general. So I don't particularly like variance and standard deviation. We've gone over that by now, right? We've talked about our variance, that those formulas are all in the data booklet. However, the standard deviation, what do we got to do? Well, we got to find the square root of it. And then interquartile range is what we're going to talk about now. So we're now going to talk about interquartile range. And we get these kind of, when we're talking about continuous random variables, we get these weird properties where the probability that it's between two standard deviations of the center, which is the mean, is going to be approximately 0.95. And we're going to go into this more when we talk about the normal distribution. And this is kind of a golden rule that we just use to go, okay, the probability that it's between two standard deviations of the mean is 0.95. But IQR, okay. So IQR is the range of the middle 50% of the distribution. So if you were to only look at the middle 50% of the values, if they were in order of x, what is that range, and it helps to show how much spread we've got. And we can actually use it, as I'm sure you know in biology and chemistry and physics, remove outliers as well if they're too far outside. But you don't need to know that as I'm aware. Okay, so IQR is the difference between the 75th percentile Q3 and the 25th percentile Q1. And this is a formula that you do have to memorize. This one is not on the data booklet, so you are going to have to memorize this one, unfortunately. But it's pretty simple. It's just IQR equals Q3 minus Q1. Okay, so an example of this would be, determine the interquartile range of the random variable x, which has the probability density function of f of x. So 2 of x, 2x between 0 and 1, and then 0 for everything else. We would have to find the 25th and 75%, percentiles. Um, and to do that, we would sub in that the probability that it's less than A is 0.25. It's a similar concept to when we were talking about median, right? Except this time we're talking about Q1 and Q3. Q1 being 25%, 75 for Q3. So yeah, we just solve for those two. We find that A equals 0.5, so that's for the Q1. Then we solve for B, and we find that it is equal to 0.866. Therefore, interquartile range is 0.366. Okay, cumulative distribution function. So we're almost at the end now. We are getting there. Cumulative density functions are the application of probability density functions. It's like the probability that a random variable x is less than x, different x's. Sorry, I've written that wrong. But yeah, so a cumulative density function, f of x, is the probability that x is less than x, a capital X there. And it equals the integral between the lower bound, c, and x. So if we have this value x here, we're finding the integral, the area, under this curve. Between that and the lower bounds, the c would be here for the lower bound. We're finding the probability that it's between there and there. The probability that the random variable x takes a value of less or equal to x. And you have to memorize this formula that capital F of x, so the capital is for the cumulative density function. When we're talking about a cumulative density function, we are talking about capital F of x as opposed to lowercase f of x. Now, one thing I will note is because it gets confusing with variables, and we are talking about an x, what we do is we actually let the first x from the probability density function be t. So we make that f of t, and then we integrate in terms of dt. So you'll see that in the steps of this next question I do, but essentially you got to make sure it's in terms of t. Otherwise, it's going to get confusing. We have two x's, and your working out is going to be wrong. So yeah, just key things to memorize here: that formula and the fact that c is our lower bound. You are going to have to memorize that, unfortunately. And also the understanding for this. So what I want you to understand in terms of understanding is when we're talking about cumulative density function, it's giving us the probability that x is greater or is less than x. Capital X is less or equal to x. So it's just kind of simplifying what you could work out using a probability density function. But what happens is the cumulative density function is going to be this nice like linear formula or something because we've already done the integration. So you might have like several questions, and if we've already done the cumulative density function, what we can do is save a lot of time because we don't have to do the probability density function each time. So yes, you're like, what's the point? What's the point? The point is that we save ourselves a lot of time when we've got repeat questions for what's the probability that this is less than that? What is the probability that x is less than this? That's why we do this. Okay. Important properties of a cumulative distribution function. So the probability that x takes a value of less or equal to c is 0, i.e. the probability of c is 0. That's just saying c is the lower bound, whether that be negative infinity, 0, whatever. 2, the probability that x takes a value of greater or equal to d is 1, i.e. the function of d equals 1. The probability that f of x is going to be less than d is 1. This is basically just saying that d is the upper bound. So if x1 and x2 are values of x with x1 greater than x2, then that means that the probability density function where x is less or equal to 1 is greater or equal to that of x less equal to x2. And that one, that's a little point I got in there. Once again, if you're a maths brainiac, that'll help your understanding. If not, that's still fine. It's not a key concept I want you to understand. Those first two are though. Okay. Cool. So this would be an example of a cumulative density function, and that final point relates in here. So it's not decreasing. A cumulative density function doesn't actually decrease. A cumulative density function is always increasing. And it goes up to 1. It's limited between the bounds of 0 and 1 because on its y-axis is its maximum probability can only be 1. And because it's cumulative, we're actually taking into account the integral. So it is going to get up to 1 as opposed to a probability density function, which is only going to get up to whatever the highest point is, like the mean. So yeah, function f is a non-decreasing function. Okay, great. Now let's go through an example. And looky here, we've got two different probabilities here. That's why we're going to do the cumulative density function, besides the fact that they've also asked us, which means that, we do have to do it. Okay, so example. The time taken to complete a maths quiz is a random variable with a density function given by f of x equals 5 over x squared, where x is greater or equal to 5, and 0 elsewise. So random variable, it is continuous because it's a function, and a function means that it's continuous. It's a smooth line, which is continuous. Question 1 is asking us to find capital F of x, the cumulative distribution function of x. And I will note that cumulative distribution function is CDF as opposed to PDF for probability distribution function. So, working this out. Well, we're given that f of x above. To find f of x, you'll remember that the formula, the one that you're supposed to memorize, is we integrate between the bounds of c to x. So we kind of we have to let the original one be t. So we replace the x in that f of x equation to be f of t. We make 5 over x squared to be 5 over t squared. And then we sub x in as a variable in that integral. So we actually integrate between the lower bound, which was 5, and the upper bound, which is now x. And we integrate in terms of t. And then that'll give us a function where we can sub in different values of x, which is pretty cool. So f of x equals capital F of x, cumulative density function, equals the integral between 5 and x of f of t dt. We integrate that, and what we wind up getting is, and then when we sub in the x, which is just a constant in this case, we get the cumulative density function equals 1 take 5 over x for x being greater or equal to 5. And now, when we do our next steps, instead of having to work out when we have this less than stuff, we don't actually have to work it out each time and integrate each time. We've integrated once. And the reason this is really handy is we can just sub in different values of x to find the probability that it's going to be less than that, which is really handy. And this is how we'd write capital F of x for the cumulative distribution function. Okay. Now we use the cumulative distribution function to find the probability that x is less or equal to 7. Remembering it doesn't matter if it's x is less than 7 or x is less or equal to 7, or even if it was x is greater than 7, we would do 1 minus that probability, right, to calculate that. And that's what question 2 is doing as well. So what we do is, because we've already worked out the cumulative density function, all we do is just sub in 7. So probability of x is less or equal to 7 equals f of 7, capital F of 7, which is 1 minus 5 over 7, we just sub in x equals 7, which equals 2/7. Alternatively, as we've got in question 2, part 2 of this question, or part B, is a question asking what is the probability that x is greater or equal to 6? Now, this one you need a little bit of thinking, and that is that you have to remember that the probability that it's always one minus. So this is kind of two outcomes. It's always binomial because it's like it's either greater or equal to 6 here. Can't equal 6, by the way. Reason it can't equal 6 is because we're talking about cumulative density function, so it's going to be like infinitely detailed. So the probability of x equals 6 is 0. Remembering that golden rule that we were talking about before, and you have to extrapolate with these questions as well. So the probability that x is greater or equal to 6 is equal to the probability of x being less than 6. Or, i.e., now we can use our cheeky little cumulative density function. That is the probability that of 1 minus f of 6. Sub in f equals 6, x equals 6, and what do we get? Well, we're going to have 5/6, and what are we going to be left with? 1 minus 1/6, which equals 5/6. Okay, now we're going to talk about the normal distribution. So there's several properties to the normal distribution that I really want you to be comfortable with and very confident with when you answer them. Number one is that the distribution is symmetrical to the mean. Secondly, I want you to know that it is bell-shaped and that the mean and median are both equal. That tallest point, that middle of that graph, is going to be the mean and the median, okay? These are the key concepts of normal distributions. A normal distribution is just something that we see in nature, and when we have massive population sizes, that is almost the norm. It's the normal, hence why it's called the normal distribution. Normal distributions are also continuous because we've got a smooth function that defines it, don't we? But it's just the most common one that we see in nature, and there's different rules we can use to determine them. They're their own thing. They're the final thing that we're going to be talking about today. So well done for sticking with me. We are going to get through this. Okay, normal distribution. It is a special continuous random variable x, which is a normal random variable, with a probability density function of this. You do not need to know this probability density function. Just know that that's the normal one. Maybe it comes up in multi-choice. That weird expression describes a normal random variable. And we have these different properties of it and these different values, which we're just going to memorize, but we can just know tech-free the probabilities, and we're going to go into those in a second. So if x is a normally distributed random variable, the PDF is given by, I need to memorize this, just make sure you know where to find the norms PDF, which is from my calculator. But if you're finding probabilities, you would also need to, or norm CDF exam, for example, you should look up what these equivalent functions would be on your calculator to calculate the probability. But there are these different properties. They both still have the mean or median, because they're the same, and the sample deviation, which is standard deviation, which is just S. And you can see those in this formula. We have S here and the mean here. Okay, so an example would be sketch the normal distribution and the normal distribution width. So where mean equals 1 and S equals 1, what I've done is I've just got Desmos here and changed it. And as we can see, if the mean is 1, that means that the peak is going to occur at 1. For the second one, the peak is also still 1, so the peak is still the same, still 1. But because the standard deviation is 3, we have a much wider interval for which most of the values lie. And we're going to talk more in depth in just a minute about what those different rules are. So we have this PDF to describe a normal random variable x, and we can work out the probability between different points using norm CDF, norm PDF, etc. that I want you to ask your lecturer about, or do some Googling as well, because I don't want to tell you a wrong answer. But essentially what you can do is you can find the probability that it lies between two different functions, similarly to like you would do with our integrals and stuff like that. So the mean here would be 4, and the standard deviation would be 1. That's just applying the formula. I really doubt you get a question like this. This is just for show, to show you that we can get questions like this. Okay, Standardization. So you're seeing red. That means that you have to memorize these things, and they are really critical that you memorize these. A lot of people actually leave this off their study and don't do well because of it. So for a normally distributed data set, um, we use these following approximations, and that is that 68% lie within one standard deviation. One standard deviation means either side of the mean, one standard deviation. So our little S symbol, really. And within that one standard deviation, so over here, that area is going to be 0.68. So you can write 0.68 on this graph. Then we have that 95% lie within two standard deviations. So between here and here. So 0.95 is the probability here. And of course, if we were to integrate between here and here, or do norm norm PDF between negative infinity and positive infinity, you get 1. The probability is going to be 1, isn't it? So 95% lie between here and here is 0.95 because this, and then 99.7% lie between three standard deviations. So between here and here, 0.997 is the area of there. And you can see, I would recommend writing this and memorizing little distinctions here, because sometimes you'll get weird questions, and we might go into some, where you have like different, you'll be given, and you're like, I'll find the probability that's from here to here. And you have to know these little distinctions to know what to minus away from one. So like 0.34, for example. And this is known as the 68, 95, 99.7% rule. And it is something that is a key learning objective for me for the syllabus. You need to know this. And we're going to go into it in a bit more detail now. So this is once again showing that empirical rule that you just have to memorize. I'm not going to repeat myself again. But what we have are these different Z values, and Z is talking about how many standard deviations it is away from the mean. So when I'm talking about a Z value, what I want you to understand simply is we're talking about how many standard deviations away from the mean it is. So Z equals -3, three standard deviations that way from the mean. Alternatively, two here, Z equals 2, two standard deviations that way. And then we have our probability. Area under this would all be 1. And this is called standardization as per the 68, 95, 99.7% rule. Example. Okay, so the scores on a maths test can be assumed to be normally distributed. So we're going to be talking about what? Norm PDF, norm CDF, depending on your calculator, with mean of 50 and S equals 5. What percentage of scores lie above 55? Well, we would write this like probability of x being greater than 55 is the probability that x is greater than 50 plus 5, which is of course equal to the probability that it's greater than the mean plus s, just 1. So we're looking from the probability that it's above here. So 13.5 plus 2.35 plus this equals 16%. Alternatively, we've got find the probability that x is less than 45. 45 is equal to the mean minus 5. So here, and it's below here, so we're looking at this 13.5 plus 2.35 plus 0.15, which also equals 16%, or 0.16. Then we're looking for the probability that x is above 60. 60 is 50, the mean, plus 2 times 5, or the mean plus 2 standard deviations. So we're looking for, above here, we're looking for 2.35% plus 0.185%. We get 2.28% there, or 0.0228. Standardized values. So this is what I was talking about before, Z values. You need to memorize this formula. This is the formula for Z, and all it's saying, so Z is just how many Z values we are away from the mean, and you do need to memorize this. So Z equals X, the X value we're looking at, minus the mean divided by the standard deviation. And if Z is positive, this means that the result's going to be above the mean, whereas Z is negative, this means that the result is below the mean, and we can see how many standard deviations it is away according to this formula. You do need to know this formula because sometimes we get complex, familiar and unfamiliar questions where you're asked to find certain things, the mean of the standard deviation, given the Z score, or the x, or you sometimes have to work it out as well. Or because z is related to probability, you might be given the probability that something is less than something else, and you have to convert it to z first. If you're looking for more info on that, definitely go to the topic test book, and it will be a complex, familiar, unfamiliar example. Or, of course, um, request a tutor, and you definitely go through it as well. Okay, so the height of grade 8 boys in a certain high school, so this is an example, is normally distributed with a mean of 160 and a standard deviation of 10. What is the standardized value for the height of a boy who's 155, 180, and 172? Well, standardized value equals z. We're asking for how many standard deviations there are away from the mean. So all we do is sub in that the mean is 160, s equals 10, using that formula. And what do we get? And then we sub in the different values of x, and they give us these different values. And because these are all negative, that means that these boys are all, well, except for those last two. I've made a mistake there. I've got two negative signs when it should be positive. So that's my bad. These values should all be, that means that this is, so essentially z is how many standard deviations are we away from the mean. Okay, determining normal probability. So we can use a graphics calculator, as I said before, to find probabilities of it being 1, 2, 3 standard deviations from the mean. So x is a standard normal variable. And if x is a standard normal variable, this means that, so if we're talking about a standard normal variable, that means, and you got to memorize this, that the mean equals 0 and the standard deviation equals 1. So if you hear standard normal variable, think that we're talking about mean equals 0, standard deviation equals 1. And we can then use z values to determine the probability that it's between -1 and 2.5, or that z is greater than 1. So one thing to note is when you're doing, because you're using norm CDF, the graphics calculator only does calculations with it in less than. So you have to convert it to probability of it being less than C, even if you're given greater than C, such as question 2. And so you have to minus it from 1 initially to get it to that format. So here, if we're finding the probability that z is between -1 and 2.5, well, to do that, we first of all find the probability that z is less than 2.5 minus the probability that z is greater than 1 equals 0.938 minus 0.1587. How I calculate those probabilities is using the calculator, but you also have to memorize them. Not yet, not now, but in the final lecture, we're going to go through the values you've got to memorize, the final lectures being the end of the year, so not yet, and then you would work it out. Yeah, and that's just because we're trying to, so we find the probability it's greater than 2.5 minus the probability it's less than 1, and that gives us this value. Okay, probability of z being greater than 1, well, because it's the inverse, again, it's got to be less than. We get 1 minus the probability of z being less than 1, which equals 1 minus 0.8413 equals 0.1487. Now, remember, if you have any questions at all about any of the content, feel free to reach out. And also, I know the live chat will be ending soon, but you've still got a couple of minutes where you can type any frantic questions. Just screenshot the question or whatever it is, or just type it out and let me know if you have any questions. So yeah, probability of z being greater than a equals the probability equals 1 minus the probability of z being less or equal to a, or equal to. So that's something you have to memorize as well. And also, because due to the symmetry of the normal curve, we get that the probability that z is greater or less than, or equal to -a equals the probability that z is greater than a. So that's kind of represented down here. We've got these two shaded sections. And these two shaded sections actually have the same probability. And then we get that probability minus probability between -a and +a is 1 minus 2 times the probability of z being less or equal to a. And the inverse, because there's two of these shaded sections essentially. So an example would be to find following properties. If Z was a standard normal random variable between those two. So you would have to use the norm CDF function or PDF. But yeah, you will memorize these values at some point, and then ditto for the 1.5. Okay. So in summary, we went over quite a lot today. This was a very hectic kind of lesson, and there is more to go over in confidence intervals. Now, differentiating between them, honestly, you kind of learn the tricks um, for differentiating between them. It's all about practice. And going over these slides can definitely help. However, it's about practice. And you need to be practicing significantly um, to be able to differentiate between these problems. Like if you put in the work, do the homework, put in the work, you will do well for these questions and when these questions come up. Okay. So yeah, the things we went over today: Bernoulli sequences, binomial distributions, continuous random variables, normal distribution. Some reminders: if you're in methods, you are smart. So if you study consistently, practice those complex questions, stretch your understanding, and like try and be as relaxed as possible. If that means limiting caffeine intake, that's necessary. You will do well on the external exam. Believe me, like it is relative to work. It's directly proportional to the amount of effort you put in. And I don't mean like effort practicing the same simple questions over and over again. If you understand it, you understand it. I don't think you should do every syllabus, every textbook question. I believe that high yield is doing the more complex questions and like because you kind of get this trickle down understanding. But yeah, thank you for listening. I know it was pretty hectic. But well done for staying tuned. My recommendation is when you hit your external exam study, hopefully before that term 4 break, go over this again, just to remind yourself, go over the other lectures as well. And what that should hopefully do is get you conceptually to the right level so that then when you're doing practice questions, you can learn the basics and then you apply it to the complex unfamiliar as well. As always, if you need any help, reach out via our website. We have many fantastic tutors available that can give you a hand with study. I, for example, am a tutor, and we have lots of amazing tutors who do very well, who have a very good conceptual understanding to help you out with whatever questions you have week on week. We also have a methods class as well that's run every week. And yeah, that's all. Thank you for listening. And good luck with your studies. Believe in yourself, you have got this.